Imad, could you please like tell us the guidelines of the projects because I missed it. I didn't find it in the record.
Oh, it's a very basic project that is related to machine learning in any way, shape, or form. So anything you're doing about machine learning is accepted. So for example, if you're already working on something outside this course that is highly related to machine learning, that could be your project. If you're not, then try to think about, I don't know, anything that is related to machine learning. I will give you some ideas, but preferably it should come from you guys first.
Okay, so we have the project, midterm, and the final, right? Or
Yes. Yep.
oh, okay,
And two homeworks.
okay.
Yeah. The homeworks are quite basic. I think we can start right now. Let's go for it. So for today's lab, I'm not going to be using anything that I have created beforehand. So everything is going to be done from scratch right now. Okay. So the first one, as we discussed during the lecture, will be Detectron 2. So Detectron 2 is a Facebook AI research library that provides us with a lot of computer vision models. And it's pretty intuitive to use. So only thing you have to do is go to Google, type the word Detectron 2. And the first link is their GitHub. You come into their GitHub. Quite nice. This is the structure, everything.
I
Yes.
think we have problem with the screen. Like we
You
see
can't see
your
it?
Telegram.
Wow. Okay. That's weird. Thanks for telling me, guys. Can you see this?
Yes, GitHub.
Okay. That's cool. Okay. So as I was saying, so go to Google, just type in Detectron 2, and the first link that you get will send you directly to their GitHub. The GitHub is quite lengthy and it has a lot of documentation that I couldn't see about their projects. Let's see, for example, here are the projects. Here you could see all the things that you could do using Detectron. So for example, dense pose estimation in the wild, a scale aware TRIDNet networks for object detection, tensor mask, a foundation, dense object segmentation, mesh RCNN, pointed rend, which is image segmentation as rendering, momentum contrasting, as just a lot of different things that you can do. For today's lab, we're just going to do basic object detection. And in order to do that, you could just come here to the Colab notebook. Is everybody like used to using Colab notebooks?
Yes, of course.
Okay, that's nice. So this is what a Colab notebook environment looks like. So it's basically a what is that called? A Jupyter notebook that is hosted on Google Cloud. So basically, it's like free computations. You can get free GPUs. You see, so you get free GPUs for free, and it's quite fast. So that's great. The first simple thing. So all of this code, by the way, is given to us directly by Google. I haven't written any word in this code. This is all Google's code, right? And we can use it immediately. So let's start. So the first part is to install basically the basic, what are they called? The basic requirements and of course the Detectron 2 itself. Everything is also handled by Google, by Facebook, because they make sure that every time, for example, Colab changes its like requirements or changes its installation, they always fix this installation code. So you're good with that. Installing it from scratch on like a server or something else is quite tedious, but on Google Colab, it's always done for you. So that's good news. Here, we're just making sure that everything is good. So first, we check that there is a compiler, CUDA compiler. So you have like the GPU and you have access to it. The Torch version is 1.13 and the CUDA is 1.16. And the Detectron version is 0.6. So as you can see, it's still not like a real product out there. It's just in the zero phase, right? Basic imports. For now, we're not going to discuss what each and individual thing is. We will, once we start seeing and interacting with these, we will see them during the code, okay? First, basic example is how to run a pre-trained Detectron 2 model on a single image. So say, for example, you have this image. If you guys have any other image that you would like to test, please send it. Let's use something maybe that you guys are used to seeing. I don't know. Innopolis. Does anybody have like an image from, I don't know, Innopolis staff or something like that that we could use? Oh, here, this one looks good on Contacte. Okay, so let's use this. Hope this works. No, it doesn't work. Why doesn't it? Still doesn't work. I have no idea what this error is, so let's just continue without it. Oh. Oh, wow. Awesome. Let's check if it works well. Yeah, it does. Check. Let's do this. Okay. Again. Wow. So apparently it's a problem with. Okay, let's just try to run all here. So there's a problem with Colab. For some reason, it doesn't work with wget anymore.
Then try urllib, but
Yeah, that's
download. So here is the code.
Ooh. Looks amazing. Let's try it. Huh? Sorry. Okay. And then let's try with this image. Just to see if it works or not. And then let's use this. Yeah, so here it works, but over there it doesn't. Well, lovely. Let's just close this session and how to this. Let's come back here. So this is the image that we're using. I don't know these two students, but they're probably inaudible students, right? Now let's use our model. And visualize it. So before we get into detail on how did we do this, let's just look at what the output of this is. So yeah, the model is not perfect. So it considered this as a person and this as another person. And this is a chair, correct. And this is a person, this is a laptop, a laptop, a laptop, a laptop. So what you can see first is the percentage of these good objects is high. The confidence is quite high. 100, laptop 95, 92. Let's see, this is 94%, a mouse 83%. But this bad duplication is at 66%. This is scissors, which is not correct, but this is a book, also kind of not correct. But can somebody tell me what is this problem that we are looking at right now? The same object predicted twice. So we have the same object predicted here. And then again predicted here. But it's, as we can see, it's the same person.
So object segmentation, I guess, right?
This is object segmentation, yes, but what is the problem of detecting the same object twice, and how can we solve it? So what didn't work in this situation? There is a step that we usually perform to get rid of this issue, but it didn't work. Okay, somebody from the lecture, what is that?
Suppression.
Perfect, non-maximal suppression. So non-maximum suppression here did not work, mainly because the second prediction did not take into account the full object, right? So we used intersection over union to do this calculation, but sadly, since the intersection over union of this one is not perfect, it doesn't give good results. So this is a clear example of non-maximal suppression failing to, give the good results that we expected to give. But in order to improve a little bit the results, one could simply take this threshold and put it 0.9. Let's try again and see what happens. Sorry. So now it's a bit better. So it's a bit cleaner, as we can see. It only shows you the things that it's absolutely certain are true. And the results are quite nice. So this one, for example, this mouse was not predicted, this mouse was not predicted, but still everything else looks okay. Now let's look back at the code and see what did we do. So the first thing we did was to get config. So this gets the default config file. In order to make a predictor, we need this config concept. Either you have a config file, or you basically build it through, through the Python code. The config file is quite simple. Let's try if we can access it. We can't do it here, but let's do it here, I guess. Yep. Let's just get it. Oh, it's not implemented like this. Okay. Well, it's just basically a project-specific configuration that tells you what is the what is the architecture of the model you want to use, and what are its hyperparameters, and of course, where can we find the weights if the weights exist. So here we can define the architecture of the model. There are so many models in the model zoo. So if we want to go to the model zoo of Detectron and see what they have. Yeah, I think they have like quite a lot of different files. So these are like basic faster RCNN models, different versions of them. This is another Retina model, fast RCNN and RPN. Remember these? This is for segmentation and for instance segmentation. This is again for instance segmentation, instance segmentation, instance segmentation. Other settings. Yeah, this is all the models that we have, at least for now, in the Model Zoo. I think they have a little bit more for other projects if you want to go to other projects. Yeah, and you can find a bit more. But basically, the Model Zoo allows you to define which architecture that you want to use. And of course, what are the trained weights that you would like to use. As you know, training a big object detector from scratch is quite impossible for us to do. And there's never going to be enough data for us actually to train basically an object detection model like from scratch. So the best thing to do is to use the checkpoints that are already also existent in the Model Zoo that are trained on different data sets. You can come here and see that some of them are trained on Pascal data set, some of them are trained on segmentation, some of them are trained on object detection. It depends on what you want to do basically, but they're quite similar, all of them together. And here you can find some explanation on what the differences are between the different models. But for now, we're going to be using Mask RCNN R50 FBN 3X. So that's the architecture we're using for today. This is how you define the threshold for this model. So config.model, what is ROI heads? What is ROI?
Region of interest.
Nice. What are the heads? You know what? Let's look at the model, right? Let's look at the model. See its architecture. No, it doesn't do it like that. I think it's dot model, right? Yeah, here's the model. So let's look at the architecture and somebody tell me, where are we, right? So we're using a generalized RCNN. This is the name of the what is it called, of the class. The first part is this one, a backbone called FBN. Goes through some bottlenecks, the ResNet, and then another ResNet, and then another ResNet, another ResNet, and then we have an RPN. What is this name? What is this name? Anybody can tell me what is RPN?
Region proposal method.
Perfect. What is the region proposal? When was it introduced?
Like where we are trying to find objects. We propose some regions where we want to detect them.
Perfect. And it was introduced in faster RCNN, right? So the only difference between faster RCNN and mask RCNN is this mask head. So we are going to ignore this mask head for now. Everything else is here for us. So we have a box predictor, which basically spits out the, what are they called? The location of the boxes. We have a box head and a box pooler. This is the ROI head. And this is the RPN head. What we are configuring here is the ROI heads threshold, right? So the RPN head predicts the, let's get our faster RCNN architecture here. RCNN. Yeah. This is the one. So this is the paper for faster RCNN. If we go down, yeah, so these are what they are calling the RPN heads. So the RPN heads are basically the anchors that we're using, and of course, they're classifiers. For what we were handling with the ROI heads is the final part of the classification. I'm not sure if they have the architecture here, the full architecture here, but yeah, they don't have it. They didn't put it. Yeah. Well, that's sad news. But basically, FPN is this feature pyramids network. If you have done the computer vision course already, you have already seen how we leverage pyramids. So basically, this is just a new way to do convolutions instead of just doing the prediction at the final level of the convolution. Now we're doing this feature pyramid at each step. So this is basic convolution. Here it's basic deconvolution, and we're doing predictions at multiple steps of the network. This allows the signal to go much deeper through the network, but this is just a basic convolutional neural network that is used as the backbone for the predictions, right? So previously we said that they used VGG. You can use any type of convolutional network as the backbone for the predictions, but I would like to see the full architecture somewhere. Here's the image. Yep, this is a beautiful image. Yes, so these are the ROI heads that we were configuring. So this is the ROI head that we were configuring. This is the head that comes after the ROI pooling. And this is what we were giving the threshold to, right? So when you come back here, and we're here, right? So when we're setting the threshold for the test here, this is the threshold for what is an acceptable object that we can show, right? So if we come here, we only show the objects which the model is at least 90% sure about. So this is the testing threshold for the object classification at the end. So it's not for the region of interest proposal. This is for the object of interest at the end. If you would like to set the threshold for the region proposal, there's definitely some sort of, I think it's called RPN heads, threshold, something. Let's see. Yeah, this is RPN head, some sort of thresholding there. Yep. Let's come back. Yeah, so we said we get the architecture from here. We get the checkpoint from the model zoo. Also, we set some configs. There are hundreds of other configs that we can set later. For example, the location of the test dataset, the location of the training dataset, and other things. So here, thanks to our friends at Facebook, they have developed multiple classes or multiple wrappers around these objects that would allow you to do different things. So for example, if you're just interested in the predictions and you would like to deploy something, then you could use the default predictor. So the default predictor gives you just one object, and through that object, you can treat it as a model. As you have seen here, it is a very Pythonic and very PyTorchic implementation. I'm not sure if you guys are familiar with PyTorch, but as you know, with PyTorch, you have access to everything all the time. So for example, if you would like to enter the predictor and go to the model, you can go from the model to the, let's say, backbone, not the backbone. Let's go to something that we wanted to see before. Proposal generator. Here, we have access to the proposal generator. We want to go even deeper. Let's go even deeper. RPN head. And this allows you to go deeper and deeper and deeper to any object inside your architecture. And you can see those layers, you can access them. Of course, this is just a string that you can read, but this is an object that you can interact with. You can change it. You can set it to a different layer, or you can change the number of the output, change the input size, change anything that you would like to change, and it's fully flexible just like that. So this is the power of PyTorch. I'm not sure if you guys are all familiar with PyTorch, but this is what makes it basically very flexible for research. As we can see, we just call the predictor on our image. It has already a wrapper that takes into account, so basically this image, and it converts it into tensors, and everything is done for you behind the scenes. So instead of like having manually basically convert this image into a PyTorch tensor, and then from that PyTorch tensor create some sort of a batch, and then the batch goes into the predictor, and all of this is handled for you in the background through this default predictor. All you have to do is just send it an image, and it will do the predictions for you. So as you can see, it spits out an outputs variable. And this outputs variable, let's look at what it contains. So here we have the predicted classes. As you can see, we have 2 boys, 1 laptop, 2 laptops, 3 laptops, 2 persons, and 1 chair and 1 mouse. So here we can see that at least 63 is repeated 3 times. So this is the laptop. We have 0 and 0 repeated twice, which is for person. And then 64 is probably a mouse, and 65 is a chair, or 56 is a chair, or something like that. But if you'd like to learn a bit more about what the output of this of these models look like, then usually they contain these instances objects, which contains the predicted boxes, the locations of all the boxes of all the objects. The scores, it's basically how confident the model is about that specific object. Predicted class, it's from 0 to number of categories and depends on what data set it was used to train. So just go to that data set and they will tell you what is class number 0, class number 1, class number, etc., etc. The predicted masks, if you are doing segmentation, predicted key points, if you are doing key point detection, and of course, some segmentation proposals here, but this is not what we are interested in. Panoptic segmentation in case also if you are working on panoptic segmentation, but for us, it's mainly this that interests us. So here we go into outputs instance. So let's check what outputs in general looks like, right? So here we see that it contains this instances object. The instances object tells you we have 7 instances. We have 7 objects located in that image, some details about the image, and then immediately comes to the location of the boxes. So as you can see, this is the X, Y, and the width and height of the objects. So all of them are numbers. So this is the regression part. And then here we see the score of confidence. All of them are above 90 because we set that score threshold. And then here are the classes or the categories. So this one is classification part. And then again, the predicted masks. And this is how we predict the mask of these objects. And it's a very simple thing. Basically, every pixel that doesn't belong to the object will be set to false. And every pixel that does belong to the object will be set to true. And that gives you this coloration of the object's location. So we've seen the predicted classes, we've seen the predicted boxes. Now let's go and see what we can do with this, right? So the first thing we're going to do is the following. Let's figure out what is inside config.datasets. So config.datasets, the training dataset that was used is COCO 2017. And the name of the, what are they called? The name of the objects is being extracted or being learned through this name, right? So previously, we were saying category 0, category 63, and the model using this information that we merged previously in here is able to find the name of all of these objects. Later on, we will see how we'll be like creating basically this metadata catalog instead of just getting it through the name of this predetermined, what is it called? Predetermined data set. So let's look at the config in general, right? So this is the config in general, how it looks like. It's quite ugly. So it tells you the configuration version. The model is here. So proposals false, mask on true, key points false, device is on CUDA, meta architecture is generalized RCNN, the weights are found in this location. Pixel mean is there. Pixel standard deviation is here. So this is the, what is it called? The channel for red, green, and blue. This is how they are standardizing the images. The backbone is a build ResNet FPN. So it's an FPN or feature pyramid network that is based on FPN on ResNet. As we said, ResNet is one of the ImageNet proposals, and we haven't really went deeply into the differences between ResNet and VGG and others, but we will do that maybe by the end of the course. And here you can see lots of other information about your config. We didn't set any of these values. They're all merged by default from this file, but later on we will see how we can change some of these values. Let me check if we could, not the ROI head, what is it called? ROI key point head, ROI in box, cascade head, ROI in line, ROI mask head. Where's the RPN head? Yeah, it's called RPN head. Nope, not here, not here, not here. Go up. Standard RPN, let's say threshold then. Okay, so we have intersection over union thresholds, boundary threshold, non-maximum suppression threshold. So this is the threshold. Remember the N that we were seeing in the lecture. So you can set it here. The score threshold test, non-maximum threshold test, intersection threshold, overlap thresholds, non-maximum. So you can see it any what is it called? Hyperparameter that you would like to change in this model. You can change it through either the config file version that is text version directly, or you could set it through just basic Python code. And here we come back. We have the visualizer that does this visualization. No need to go into depth on how does it do the drawing and all of that. So this is just some Python code that adds basically some layers onto your image. So it's basic Python. Now we get to the real part, right? So the real part is the preparation of the data set. This is a data set that they are using, or that they have given us. It's called a balloon data set. It's a very small data set that you can see is 36 megabytes. And of course, it's not even barely usable to train an actually good model, but it is good to fine tune a smaller model. So, or a trained model, sorry. Again, I have this issue. I think it's, yeah, it's an issue with all of these. I would have to restart the runtime, but I don't want to do that because I've already ran the code and it works very well. I don't want to do it again. So just assume that we downloaded this data set and we unzipped it. And once that happens, so let's download it, right? I think I already did. Just for the sake of seeing this data set, we're going to go to this RoboFlow and we're going to upload it here. So it's a balloon data set. Object names are balloons and the license is this. And we will upload a folder, a balloon data set. Yep. Here it is processing these images. There we go. So it's not, it's segmentation. It's not object detection. Okay, no worries, right? Save and continue. Yes. So this is RoboFlow. RoboFlow is basically a library that allows you to handle data sets, right? So it allows you to annotate data. It allows you to upload new images, annotate them, collaborate with your friends. And in the end, you can create different versions, basically different processing. You can do some augmentation. You can change you can flip the images, rotate them, crop them, rotation in, shear, grayscale, hue, do any of these augmentations. You can rotate just an object, not the whole image, but only the objects, flip them, rotate some objects, shear some objects, blur only the object. So the image is not blurred, but the object we're looking for is blurred, noise them, explode. So you can do anything you want to these images. And finally, you can generate a data set that is compatible with Detectron that is compatible with any version of YOLO out there, that is compatible with any version of object detection model out there. So no work needs to be done for, well, at least this part that we will be seeing. So this is the data set that we have. Let's try and go back just to see it. Overview, not the overview, upload, assign, annotate, data set. Here's the data set. Okay, what's happened? Yeah. Let's look at some images. So this is the images that we have. They're quite well annotated, as you can see. This is the object. Let's go to the next. See, this is it. As you can see, it's a lot of objects. Although it's a small data set, it has a lot of annotations. And that makes it good in training our model. Now, if your data set was created, let's just do this. If your data set was created through RoboFlow, then you can easily read the data set like this, send the JSON file of the data set, tell it the description of the JSON file, where it is, and the location of the images, and it will handle all of this for you. But that's not the case for us. We're using a data set that is created from scratch. So let's look at it here. Balloon data set, validation and train, and here are the images, right? So this is the image. It's a big image, so we're not going to look at it. So these are the images, and we have this validation region data set, or via region data set. And this will tell you image X or image Y. It will give it, I don't know how to walk in this image. All right, let's walk a little bit. Yeah. So it will tell you some information about the image, useless information about the image. And then it will tell you the regions. So here it will tell you the shape of, you see these all points. This is the X. Could you guys hear me, or was Siri interrupting me? Hello?
We can hear you now.
Okay, so as we were saying, we can look here and find information about the image, plus we find information about the objects of the image. So here, for example, it's a polygon, and it's split into X coordinates. And then once we finish, we'll find the Y coordinates. Yes, all points Y. So this is the these are the Y coordinates of that object. When you take X and Y from this one, you will have 1 point, and then again another point, and then again another point, and then again another point. And these points will create the contour of your object. So if I come back here, this is telling us like multiple points. So yeah, these points. This is telling us the location of all of these points that define the contour of our object. So when I come back here, what we will be doing is we will read first this JSON file. The JSON file gets loaded here. We go through all the values of this JSON file. We take the file name from the JSON file. We take the information about the height and width either from the JSON file, or we can do it from, as we're doing here, basically by reading the image and then taking the shape of that image. We give it an index, which is just a randomly generated number, or just like an iteratively generated number. And then for the regions or the annotations, we go through them one by one, and we get the following. So this is the shape attributes. This is the px point x. The py is the points y. And this is just the way to convert them into a polygon that has the following shape. So the box is the minimum point x coordinate. So let me annotate again. Zoom, where's zoom? Here's zoom. I don't know how to stop sharing. Oh, no idea. Ah, here it is. Yep. So these are the points that we are working with. So as you can see, it's here. The location of our bounding box will be the following. So it's the smallest x coordinate, so it's here. The smallest y coordinate, so it's here. So it's this intersection. And then the maximum x coordinate, which is here, and the maximum y coordinate, which is here. And this gives you the location of your object. And then again, this is how you define basically the polygon for segmentation. It's only the definition of these points. Instead of having them defined as x points alone and then y points alone, we require them to be together in this shape of x and y couples, which is just a simple, this is how they want it, right? We do the plus 0.5 just for the sake of making sure that we never get like a 0 or something like that. And then the category ID, this is very important since we have just one category in this example, which is balloon, right? So the balloon dataset only contains balloon. So it's a simple idea. What you could do is just set it to 0, and then the thing classes here is going to be the list of all the objects that you have. In our case, we only have one object, so its category ID is equal to 0. But in the cases where we have multiple objects, we will have to set, for example, if it's a human, we put 4. If it's an animal, we put 6. And then in this list, you put all the names of these objects or categories that you have. And that's it. Again, later on, you will register this data set and register how to get basically its images and annotations by doing exactly this, right? So you register it and the location of it here. And then the final part is to register that data set into the metadata catalog by adding basically the information about the object names, right? So if you don't add this, what will happen is instead of the word balloon being shown here, it will just show you index 0. It will show you just the index of that object, but when you give it the list of the objects names, it will give you the basically this, right? Which is a bit better. And here we're just verifying that we access the data correctly. So this one gets the training data set and it just randomly samples 3 of these objects and show them. And clearly we are accessing the data correctly. This is good. Now we have to train it. For the training part, it's very similar to the prediction part, right? So instead of using default predictor, we're going to be using a default trainer. We get the configs, select which config we would like to use, which saved weights we would like to use. And then here, this is the threshold somewhere. We should have the, we don't have the testing threshold here. Yes, so what we have to set here is the training dataset name. It should be the same name that you registered here. So balloon train or balloon validation. So here, balloon train, this is the training dataset. For training, we don't have to set the test dataset, but we can set it if we wanted to get like constant validation if we had a validation dataset. The number of workers, how many workers will the data loading use? This highly depends on how much CPU and RAM you have. So you can set it as big as your model allows you, to be honest, right? The weights come from here, as we said. IMS per batch. So this is the real batch size that we commonly use in deep learning. So this means how many images will go into your to your object detector at the same time. So as you can imagine, object detectors are very, very big architectures. So we can't just go around and put 64 in here and expect it to not overload the RAM. So for this one, we're going to just go with 2 as a number of our batch size, but we could go up if you have better GPU RAM, right? Base learning rate, so you could go up or down, you could make it bigger, smaller, experiment with that, depends on how many images you have, right? Then the maximum iterations is basically how many how many iterations will you train? How many times will you look at this batch size, right? So this batch size is 2 multiplied by 300. So how many images will the model see to train, which is basically 600 in this case. 600 is definitely not enough, but since our data set is like tiny, I think they have like how many? Let's come back and yeah, we have like 74 in total, right? So we have 74 images in total, meaning each image will be seen at least like 4 times or more. That's an okay number. But when you have, I don't know, 1,000 images or more, make sure that this max iterations reflect that number. Batch size per image. So this reflects the ROI head batch size. 128 is faster, and good enough for this toy data set, but the default one is 512. So this is just to make sure that we are also doing the object proposal part as fast as possible. But again, it is very RAM heavy. So if you're not using a very good laptop or very good server, please go easy on these numbers, right? And then the simplest one is number of classes. How many classes will you be using for the training? And this is quite a basic thing, right? Just to explain this one, right? So just to explain that final batch size per image. No, not so this one, right? So we're trying to explain this in the architecture. Let me bring the architecture here. And let's share again. So remember when the object proposal gives you multiple images, right? So multiple different regions. This ROI pooling is going to launch this, well, sometimes it's called a head or ROI head or the classifier or whatever you want to call it, but we're going to send different regions or different images to it. This just means that this is a basic classification. This is a basic CNN. And the scenario here is just we're sending it a batch size, right? We're sending it multiple images. How many images will we be sending it at the same time? How many proposals will we be sending it at the same time? This will affect, as we said, the speed of the model, but it will also affect the RAM consumption. So here we can see that there are different batch sizes. The first batch size is how many images will go to the region proposal algorithm, the RPN, and then how many of those proposed regions will go to this ROI head, right? So we have 2 different batch sizes, not just in, not like in, what is it called? In basic CNN classification, image classification techniques, right? So once we have set all of these configs, we come here, we set the default trainer with the configs. Resume or load, we set it to false, so every time it starts from scratch, and then we say train. You see, it's very simple, it's very basic, it doesn't require like, I don't know, back propagation. You don't need to think about all of these objects, all of these concepts, because the faster RCNN architecture is trained on different, what is it called, different steps. So it's not as basic as you might think, right? So the first step would be, I don't know, something called, let me see, I forgot those steps. But yeah, basically, so they train the RPN first, and then they train the object detector, and then they train the mask, and then it's just a different algorithm that is quite lengthy to look at, but you don't need to worry about all of these things because the default trainer will handle all of that for you, which is good, right? So all of these different architectures have different algorithms to train them. So they don't train the whole architecture as a whole, but they train different parts separately, and then they train everything as a whole. But you don't have to worry about that. And you don't have to worry every time you change, for example, from mask RCNN that is using FPN to something that is using, I don't know, VGG. You don't have to worry how that changes the training of the model. So it's pretty smooth for us, which is good news, right? So here we're doing the training. As you can see, the training is quite fast. It took 2 minutes and 10 seconds to train on this data set. But if you're going to be using a bigger data set, it will take, I don't know, somewhere around 8 to 12 hours. And if you're training on a real data set, it will take weeks and weeks, right? So this is how many instances we have, 255 balloon instances. This is not how many images we have, right? We have 61 images, but 255 instances, because each image contains multiple instances of a balloon. And here it's trying to load basically the parameters or load the weights, but it doesn't work. Why? Because this model was trained on what is it called? COCO 2017, which had, as if I'm not mistaken, like 100 or something different objects, but for us, we're using one object. So this is why it's telling you here an error or loading, skipping loading parameter, ROI heads box detector class score weight to the model due to incompatible shapes, 81 times 10,024 in the checkpoint, but 2 in the model. You might want to double check if this is not expected, but this is expected, right? We have 80 different classes in the model, but in reality, in our case, we have only 2 in this case situation, so they are not aligned. So you can see here, this is the class score weight and class score bias. They have different shapes. Here we have the bounding box detector also is different. Here it's 320 and here it's 4. So basically it's 80 times 4 and 1 times 4 in this case. And in the final part is the mask head. As we said, this is for segmentation. So we're going to leave it to the segmentation lecture and discuss it. Here it tells you how basically the training progresses, but it's better instead of looking at it here, non-maximum expression, as you can see, everything here is detailed, but it's better to come basically to this place and just look at it, right? So here you can see how the ETA in seconds is going down linearly. And here's the accuracy. It doesn't load it. I think it stopped training for something. Here's the classification loss going down, which is good. This is what we expect. The mask loss is also going down smoothly as we expected. This is the learning rate, so it goes up. So this is the scheduler of the learning rate. This is how the ROI heads are being trained. You can get all the information that you want. Total loss also should be smoothly going down. This is the sum of all the losses of our model. So as you can see, there are so many losses. We have classification loss, regression loss, mask loss because we're doing segmentation, RPN classification loss, RPN location loss. So this is the kind of regression loss, but it's not based on regression. It's not based on mean squared errors. It's based on what is it called? L1 loss, right? Let's come here and check it out. It's, if I'm not mistaken, it's an L1 loss, right? We can check it another time, but yeah, it's basically the regression of the region proposal network. This is the classification of the region proposal network, and this is the regression of the final ROI head, and this is the classification of the final ROI head. We don't speak about the segmentation loss because that's out of this today's project. And finally, now instead of using the trainer, we have the weights saved into a file that is called modelfinal.pth. And then we load that architecture and set a threshold. This is the test threshold. We set it to 0.7. And we create a default predictor over it. Do some visualization. Again, we have seen this code so far. Now we will do some evaluation based on the validation dataset. This is the COCO evaluator. It just does basically the object detection evaluation for us. And here we can see multiple results. The most important one is intersection over union, which is something that we have already seen, but this is a useless concept if you don't understand what is average precision, and most importantly, what is mean average precision. Mean average precision, where's mean average precision? Should be somewhere here. Okay, it didn't split it out. But yeah, basically the mean average precision is the mean of these different precision values. And it will tell you whether your model is doing well or not. And it is doing very nice. So the average precision on the smaller objects is quite 0, so it's useless. Average precision on the medium-sized objects is 53. Average precision on the large objects is 89, which makes sense because the bigger objects are easier to spot. So this is the average precision at a 75% threshold, and this is the 50% threshold, and this is the average precision in general. We will not go into detail about how to calculate the average precision for now, but hopefully during the next week, we will, not next week, I think it's like in 2 days, right? Let me check. Yeah, we have a lecture in like 2 days at the evening. During that lecture, we will have like a half an hour discussion on how to calculate average precision. So as you can see, precision is a concept that we already know from classification, but how can we convert this precision concept from classification into the realm of object detection simply by using intersection over union, right? So if the intersection over union is within this range, it means it's a good intersection, it means it's a good prediction, and we can convert that object detection problem into a classification problem and basically do the matching using the precision. As I said, we will see the math behind it during the next lab, but it's quite a simple one, to be honest, right? So this tells you how to evaluate your model. We're no longer speaking about classification accuracy or about, I don't know, R2, R squared or something like that. We're speaking in terms of average precisions that are based on the concept of intersection over union. Here we can see different types of models. So this is doing balloon detection. At the same time, it's doing the key point detections. Here it's doing some segmentation, but and here you can see how you can run it on, well, basically YouTube videos, right? For the sake of going forward with our lab, let's stop. Do you guys have any questions so far? Yes or nope? About the Detectron.
No, but like everything is already written for us. So our job will be to just customize it for our case, or
Exactly. For Detectron, it's quite simple. For the Detectron, it's quite simple. Basically, you just have to customize that config file. You just have to customize this customization, right? So for example, you change the number of classes to whatever your data set is, you change the learning rate, change the max iterations and stuff like that. That's it.
and we are allowed to use it in our project, yes?
Of course, you're allowed to use it in your project, in your homework, and in your work after we finish. Yep.
Okay, thank you.
Thank you. Now,
Also,
yeah.
Yeah, sorry. So, sorry if I missed it. And what if we have some very custom objects? So for this, so and how would we adopt these pre-trained algorithms into some custom objects or some custom tasks, for example, stamp detection?
Easy. So as I said, you tell it what is the number of classes that you have. So in this case, it's 1. And when you define or register the data set, you just tell it what is the classes, right? So here, when you're registering the metadata catalog, you tell it, I am using stamp 1 or stamp version, I don't know, something like that, stamp 3, stamp 5, all the types of stamps that you have in your data set. You can either define the logic here on how to read the images of your data set in case they are defined in a weird way, or you could use directly RoboFlow, just upload it to RoboFlow. And in this versions, you can generate a new version. Let me say continue, just default stuff, right? Generate. And it's going to generate the data set here. And what you can do is, export. And here you go, all the versions that you can think of, right? So if you want to train a YOLO V8, just export it into YOLO V8 format. You want to train a YOLO V4, YOLO V4, YOLO V3 on Keras, YOLO Darknet, YOLO V4 scaled, V5, V6, V5 on PyTorch, V7 on PyTorch. If you would like to get it in a TensorFlow object detection format or any of these formats, just press it and get it in that format. So you don't need to do anything, basically. This is why RoboFlow is amazing, right?
Yes, sorry. And what if we have, I mean, just a few images and just generate thousands of images with these.
Okay,
So,
let's go back on how to generate a new version. So what you're gonna like to do the most is the augmentation part, right? So as I said, there's a lot of augmentations that you could use, and this is something that you can leverage very, very heavily. So let's say you have only, let's say, 10 images, 10 real images. And what you can do using all of these, you can set up a way to generate from those 10 images around 7,000 or 10,000 new augmented images. So it will basically take your object and, for example, changes its location in the image. It might take your different images and just merge them together in a mosaic way like this, right? So this is something that you might want to experiment with very, very heavily.
And which model, which algorithm is kind
Best?
of, can generalize better for augmented
That's a question that
images?
you will have to answer. That's your question. If you can answer this one for your task, this could be an easy research paper that gets accepted very quickly. So it's just a comparison basically between the YOLO v4 till YOLO v8, and you just print basically all of the MAPE scores for these versions on your data set. And later on, you could do some analysis saying it doesn't work for larger objects, this one works for smaller objects, etc., etc. And then that gives you a research paper. So this is a research question, right? We're assuming that every time we go further, we make the model a bit better. So YOLO v8 should be technically better than YOLO v3. But is YOLO v8 better than YOLO v4? That's a different question.
Okay.
Make sense?
Thanks. Yes.
Now, so we're going to go through the YOLO v4 code. We're not going to run it, but we're going to just do it because it's a very slow code to run. But for the sake of this finishing the lab for today, we're just going to go through the code very quickly. And then next week, we will go through the code in much more detail and run it and basically, what is it called? And run it and understand it deeper and speak about the concept of your, mean average precision, and then give you your first homework to do at home, okay? Perfect. So this is how you train, for example, if you would like to train any computer vision model that is YOLO related, so that it's not in the Tektron, I highly recommend going directly into these blogs of RoboFlow. So for example, I want to train, let's say YOLO v8, and I want to train and say RoboFlow. This is what I want to train, right? Immediately you'll find a blog post. Here it is with a video explaining everything.
YOLO v8 is out.
Yes, much better than I will ever explain it. And it's not super detailed, right? So it's a little bit, doesn't go into the theory behind, but it does give you the results. If you are trying to just get something done, it will make it work very perfectly. So let's follow along. Usually you should find some Colab notebook. Where's the Colab notebook? Oof. I think they put it somewhere here. Is the latest architecture. Architect was developed by Ultralytics and a team known for its work on YOLO v3 and YOLO v5. Following the trend, what's new? I don't know, where is it? Oh, that's weird. Usually we find a very simple, okay, let's see, Colab. Here it is. So you get this Colab notebook, and it's a very simple Colab notebook that you could just immediately run and get the follow along and basically get the results that you want. This is for YOLO v8. It's the latest version that we got, I think 2 months ago or something like that. Let me just check when was it released. YOLO v8. Yeah, I think it was like a couple of weeks ago. Not that old, to be honest. Yeah. So it's quite nice. But for today's lab, we'll just go with YOLO v4 because it's this one is probably done on PyTorch. So it's very simple and it's very similar to what we were doing like quite earlier, just like 2 minutes ago. But now we're going to speak about darknet, which is also very important for anybody doing, you know, computer vision to at least learn it exists, right? So the first step is to make sure that you have CUDA and you have like NVIDIA well configured. So here we can see that we are using CUDA version 11.6. We have a Tesla T4 GPU. How much RAM does it have? It has 16 gigabytes of RAM, which is good for free GPU. A very important thing to understand now. What is it called? Darknet is very, very C++ heavy. So it's using CUDA. CUDA is like a C++ library that allows you to do the training on, what is it called? Neural networks, etc. But it's very fast. But the thing is, it's very architecture dependent, right? So you will need to tell it a lot of information about your GPU. And how can you find this information? Either you can get it from this location. So for example, if using a Tesla K8, this is the code for it. This is the architecture for it. But that's not always the case, right? So probably when you're working in the real life, you're not going to be using any of these GPUs. So what you might want to do is simply take this name followed by the name of the GPU, whatever GPU you have, and it should tell you what is the compute value and what is the SM value. And then you take those values and basically you put them in the make file of CUDA. Let's try our best to run the code. At least you guys see what's happening, right? So first is we will download or clone the darknet code, right? And then we will create our own makefile. So makefile is just the file that you will be using in order to compile, to just give the hyperparameters, if you could say, to compile your code, right? So this is going to be compiled specifically to your GPU. And this is the arch value that we will be using. Don't forget this. So once we get that one, as you can see, it's going to be added here. I think they're going to add it at the end or somewhere like that. But basically in this code, they will be setting the correct value for the compute value and the SM value for that specific GPU. They will add it here, and then they will create this makefile. After we do that, simply we set the fact that we want to use OpenCV. So OpenCV is equal to 1 instead of OpenCV being to 0. We tell the code that we want to use GPU. So GPU is equal to 1 instead of 0. We tell it that we have QDNN. So QDNN is equal to 1 instead of 0. And we just remove this file or remove this line of code. And we set whatever architecture value we were finding in this code, right? So we set the actual value in here. After that is done, we have finally configured the makefile. What we do is we make it, right? So we run the code to get the makefile. I'm not sure where did we stop running. Yeah, I think we, oh, sorry. Yep, we cloned it. We got here, and then we got here. So now it's going to spend a lot of time compiling basically darknet to our GPU. We're probably not going to be waiting for it, but all of this is okay, right? So you're going to see a lot of code like this, which is very horrible, but it's okay. It's not that bad. Once we finish that, we go inside, we download some architecture. So these are the weights, YOLO v4 conv 137. So this is one of the different architectures that we have, or the different sizes that we have for YOLO v4. We get it. This is from RoboFlow. So if I come here Yeah, if I come here, export, I say YOLO darknet and show download code. 1, 2, 3. Yes, here it's done. It shows you the download code for that beautiful model. What you do, you come here and you spit it out. Sorry. I didn't copy it. Why it doesn't copy? Okay, now I copied. Is it finished from here? Oh, wow, it's finished. Nice. Let's stop it though, because we haven't executed this part. But anyway, so as you can see, it just gives you the code on how to load the data set. This is your data set. Immediately you load it in the format that you want. So for us, we wanted a YOLO darknet format. If we wanted to have any of these different formats, we just immediately set it like that. Yeah, so it doesn't work because we haven't run everything. But anyway, after that, what we go is we set up the config files. So there are so many config files for running YOLO v4 on darknet. The most important config files are these, right? So are the configs for the model itself. This is what we would like to look at, hopefully if we have time. But these are just basic configurations for the data set. So simply what it tells you is where is the images for the training data set, where are the images for the validation data sets, how many classes do we have? So for example, in our case, we have 1 class. So instead of 3, we put 1 in here. How many? Where's the location of the train? As I said, where's the location of the validation? And where is the object names? So object names is just basically how many objects do you have? So in our case, let's come here. It should have downloaded it here. Object names, where are the object names? Yeah, darknet.labels. These are the object names. For us, when we loaded this one, let me just verify that it's actually true. Yeah, so we didn't really give a correct name to this, so it just calls it object. So here you can see it doesn't say it's a balloon, it just calls it an object. But if we have correctly selected like the labels for the objects, it should give you the name, the list of all the objects in here. So basically, if you have 3 objects, it should tell you balloon, person, animal, etc. So this is, as I said, the location of the names of the classes. And this is just the file where you will set the backup, basically the stored weights of the trained model. That's it. Once that is done, you move to the next step, which is creating a training config for YOLO v4. This is very important. And before I go here, I would just like to look at the lecture again with you guys. Canva. Object detection. And then we go to the final slide. Yes. So remember this formula, right? We said number of classes plus 1 plus 4 for the box coordinates times 3. So this is very important because this is something that we will be setting right now. As we said, there are 3 different boxes, one for rectangular, one for horizontally, one for square, one for horizontal rectangle, and one for vertical rectangle. So there are 3 of them, and each one contains, well, number of classes because it will do classification, plus 4 for the coordinates of the object, plus 1 for the objectness score. So remember this formula, and we will come here and we will manually set that formula. So this is basic stuff, just setting the width and height of the images that we want, the number of channels, which is 3 because we're not using RGB, the batch size, the decay for the learning rate, the momentum, the angle, saturation, and exposure, and hue. This is basic hyperparameters for object detection. This is the learning rate, etc. The max batches, this is how many batches you want to basically have. So for us, we're using max batches is similar to the concept of maximum iterations. So it's at 2000. Policy, this means how many, when will we save the training? So for example, at 80% of the training, we will save a version of the model. And at 90% of the training, we will save another version of the model, just to make sure that we have something that is very, what is it called? Very easy to use, or like different options to choose from. Remember, what we said is in the lecture, again, let's go back here. Remember that we said in YOLO, the convolution itself will do the classification. So the last layer before we have this classification is going to be a convolutional layer that has an output of this shape. What does it mean, an output of a convolutional layer of this shape? It just means how many channels should that model have, right? Or should that layer have? So what we have to do is let's look at the config file. It would be better to look at it there, right? Let's look at a config file together. I think we don't have enough time, or do we have 10 minutes left? I think we have 10 minutes left, right?
Right.
Yes. So if we go to the config file, let's use a tiny version. So this is tiny YOLO, no, YOLO v4 I want. YOLO v4 tiny. Can somebody find YOLO v4 tiny? YOLO tiny, YOLO v4, YOLO 2 tiny, YOLO v3 tiny. Okay, why is it not here? They removed it? Ah, this is RoboFlow, sorry. I want darknet YOLO v4, the original one. Here, config, and tiny. Here we should have YOLO v4 tiny. Here's YOLO v4 tiny. So YOLO v4 tiny will have the architecture definition of the model, right? So as we said, YOLO is just basically a lot of convolutions following each other. Just a lot of convolutions, right? Sorry, let's go up. It's just convolutions, convolutions, convolutions. This routing is basically just how, remember when we were saying in the lecture here? So it copies this and then augments it to do the, what is it called? The upscaling, and to do this feature propagation, these residual blocks. So these are what these routes are. It's just a copying of the output from one place to another. And then again, some convolutions, convolutions, routes, convolutions, routes, convolutions, and routes, convolutions, and routes. And then we arrive, so for example, here we have some max pooling. Also, we're familiar with this one. Convolutions and routes, max pooling, convolutions and routes, and max pooling. So here we're going to do the training. So the tiny version does not have, as we see in here, 3 levels of classification, but only has 2, just for the simplification of it. What's going to happen is it will have a convolution for training, convolution, and then a final convolution before this YOLO layer. YOLO layers are only set here to do the basic classification, right? So it's just here to train the model. It's not an actual thing that will be like trained or something like that. It's just here to calculate the non-maximum suppression and stuff like that. So it's very important to correctly set the number of classes for this layer. So for example, in our case, we have 1. We must come to this place and set this value to 1. And same thing for here. And most importantly, before going here, before going to the YOLO, we must set the filters equal, or the number of channels, the number of output channels of this convolutional layer must be equal to what? 5 plus number of classes times 3. So in our case, we have just 1 class. So it's 5 plus 1, which is 6, times 3, which is 18. So we must come to this config file and change this value from 255 to 18. And again, the number of classes to 1. Same thing, we'll do it here and do this here. So if I want to verify, so for example, here we have 80 classes. Can somebody tell me 80 plus 5, which is 5, times 3? How much is that?
270, I guess.
155. It's exactly this. Remember, this is the formula. So if you just Google it or do 80 plus 5 times 3, it should give you exactly 255. In our case, we're not using 80, we're using 1. So we should change this value correspondingly. But we don't have to change everything else. So we don't have to change, for example, this convolution because it's not related to the classification part. We don't change this convolution because it's also not related to the classification part. The only thing we change is this one, right? Is this final convolution before the YOLO layer. Of course, if you are experienced, you can play around with all of these values. So the classification normalizer, intersection over union normalizer, you can play a little bit with the intersection over union loss calculation, ignore threshold, truth threshold, some randomness, resizing, greedy, non-maximum suppression. So the algorithm of non-maximum suppression that you would like to use, some of the hyperparameters of non-maximum suppression, anything that you want to play with and you know how to play with, please play with it and change it if you already know that. So this is how to define the architecture of YOLO v4. So if I come back now here, you can see that he's doing exactly the same thing, but he's doing this 3 times, not just twice, mainly because we were seeing the YOLO v4 tiny, which has 2 layers of classification. But this is the YOLO v4 custom, which is just normal YOLO v4, similar to what we have seen in the lecture. It has 3 levels. So clearly you can see in here, number of classes is equal to number of classes. And then the number of filters is equal to number of classes plus 5 times 3. And he just sets these values and moves on with his life. So here we will see the values. The training is very basic. So you can just call it like this. Darknet detector train, so it's just a command line, right? Train, you give it the location of the data object, which we created here. It just contains where is the training data, where is the validation, what is the object names and the number of classes. And of course, you give it the configuration of your architecture that you just defined, and you give it a weight file. So these weight files, we have seen that they're just loading in random weights from their location. But if you would like to have, like, for example, here we were speaking about the YOLO v4 tiny. If you would like to have the tiny weights, simply come here and you should be, yeah, it should give you, this is the tiny weights. Download the file with 29 convolutional layers. So it's quite a small one, right? So this is the tiny model, and it's only 18 megabytes. So it's quite small, quite simple. You could put it on a what is it called? On a not a laptop, on a phone, on a cell phone easily. And here's just some code to give you guys the just visualization. And if you'd like to test basically your model, you can use this darknet detect. If you would like to evaluate, there should be something called darknet evaluate. Let me just come to darknet and see it, right? Oh, I haven't deployed it yet. Yeah, I haven't built it, I think. Have we? Yeah, you should have the darknet here, but for now we don't have it because we didn't execute it fully. But yeah, so you can do, as we said, multiple things. You could do classification, detection directly, or you could do the evaluation. So this is very, as you can see, it's much more complicated than what we had for Detectron, because Detectron comes directly with this default predictor, default trainer with the visualizer. You don't have to do any code. But for Detectron, for Darknet, you have to do the code for showing the results. So as you can see, it does all the code for showing, basically printing the images and stuff like that. So it's not very cool for you, but at least now you can appreciate the beauty of Detectron and why it is very, very good, why it simplifies your life, right? So it gives you a default trainer that trains all types of different models, and it gives you lots of wrapper functions to have access to these different values. And if you would like to, here, for example, you have a bit more power. So for example, in here, if you want to actually change the architecture of your model, right? So if you wanted like a smaller model, much smaller model, you could easily come here to these configs and build whatever architecture you want, right? So this is definitely up to you. So for example, you want convolution, somebody might say, I want the convolution followed by, I don't know, followed by max pooling every single time so I can speed up the calculations. Nobody can tell you no, right? So you can build your own architecture very freely using, what is it called? Using Darknet. But again, it's very easy to make errors. Whereas in Detectron, it's more or less impossible to make a mistake in here, but it doesn't give you the absolute flexibility. So you might need to change one layer, for example, easily, but you can't just change the whole architecture in a split second. So I hope this lab was not very, very complicated for now. Again, next week, we will go back through the YOLO v4 and YOLO v8 code, and hopefully we will run it this time on a small data set, probably the same balloon data set to see, like, compare the results. And yeah, we will speak a bit more about what is mean average precision score. And that's it. So thanks a lot, guys. Do you have any questions? If you don't, then your first lab is going to be use your own data set to train a Darknet, not Darknet, to train Detectron 2 or to train a faster RCNN model on your own data set. So your own data set, it means you must go outside or, I don't know, in your room, take your phone, take lots of pictures of the same object or multiple objects if you want, I don't know, avocados. You could take pictures of vodka. You could take pictures of anything you want that is in your room or in the streets, stop signs, cars in Innopolis, anything that you want to do. Take those pictures, upload them to RoboFlow, annotate them manually, and then create an object detection model using Detectron. So as we have seen, the code is already here. There's absolutely zero skills that you need to do this. But it will take you guys some time to go outside and take those pictures and annotate them manually, but it will give you a lot of understanding about what is basically computer vision in real life. Does that make sense?
Yeah, but is it like a homework?
Yeah, this is just a homework, right? This is a basic homework. It's 12.5 of the grade.
Okay, but may you define more properly, like what you're expecting? So, like, upload a Moodle file, a file on Moodle where you explicitly says what we should do.
Yes, of course. You will have a Moodle submission link where you will have to put a report with different pictures, or either a report with different PDF reports for different pictures, or some sort of GitHub repo with a beautiful README that contains pictures of you annotating the image on RoboFlow. And I will set all the details over there, but it's basically making sure that you have taken the images, you have posted them and annotated them on RoboFlow, and that you basically did the object detection using Detectron part.
Oh, okay.
It's very basic, very simple, but I would like to see it either on GitHub, which is the best thing possible, or a PDF report with some code. Okay?
Okay, sure.
Perfect. So thanks a lot, guys, and hopefully see you, I think, in 2 days, right?
And see on Saturday.
Yep.
Okay, goodbye.
Bye-bye.